What if I told you that right now, at this very moment, there's something hurtling through our solar system that has astronomers losing sleep? Not an asteroid, not a rogue planet. Something far stranger. Something that defied every prediction we made about it. On January 2nd, 2025, something impossible happened. Comet 3I Atlas, a visitor from another star system that was supposed to be quietly leaving our neighborhood, suddenly woke up. It brightened dramatically. It developed a massive coma spanning thousands of kilometers. And here's the part that's keeping scientists up at night. It did this at a distance where comets aren't supposed to be active at all. We're talking about a celestial body that's already broken the rules of physics as we understood them. And it's not done surprising us yet. This interstellar wanderer has become what researchers are now calling an active threat to our understanding of planetary science. And before you think this is just academic hand-wringing, let me be crystal clear. What we're learning from 3I Atlas is forcing us to rewrite the textbooks on how solar systems work, how planets form, and whether we've been catastrophically wrong about what's actually out there in the darkness between stars. In the next 230 minutes, I'm going to take you on a journey that will fundamentally change how you look at the night sky. We're going to explore how a single object has shattered our confidence in predicting cosmic behavior, revealed that our solar system might be constantly bombarded by things we can't see, and suggested that the space between stars isn't empty at all, but filled with wandering worlds that could, theoretically, bring life or destruction to any solar system they pass through. By the time we're done, you'll understand why Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, said in March 2025 that 3I Atlas represents the most significant challenge to cometary science in 50 years. You'll know why NASA convened an emergency panel to reassess near-Earth object detection protocols. And you'll see why some researchers are now suggesting that Earth itself might have been visited by dozens of interstellar objects that we completely missed. This isn't science fiction. This is happening right now, and the implications are staggering. But before we dive into this cosmic mystery, do me a favor. Hit that like button right now, because this video took months of research to put together, and the algorithm needs to know you want more deep dive content like this. Subscribe and ring that notification bell, because we're about to go deep, and I mean deep, into one of the most fascinating astronomical discoveries of the decade. And drop a comment telling me where in the world you're watching from, and what time it is for you right now. Are you in Tokyo at 3 a.m., unable to sleep? Mumbai during your lunch break? London on your morning commute? I want to know, because this object is visible from different parts of Earth at different times, and your location actually matters for this story. Let's build a global community of people who aren't afraid to question what we think we know about the universe. All right, let's start with the basics, but trust me, even the basics here are wild. 3I Atlas, officially designated C 2024 S1, Atlas, is what we call an interstellar comet. That 3I designation is crucial. The I stands for interstellar, meaning this object didn't originate in our solar system. It came from somewhere else entirely. The 3 means it's only the third confirmed interstellar object we've ever detected. Let that sink in. In all of human history, with all our telescopes and all our technology, we've only confirmed 3 objects visiting us from another star system. The first was Oumuamua in 2017. That cigar-shaped mystery that sparked 1,000 theories, including the controversial suggestion by Harvard's Dr. Avi Loeb that it might have been artificial. The second was 2I Borisov in 2019, a more conventional-looking comet that behaved mostly as expected. And now we have 3I Atlas, which is rewriting the rulebook in ways that make Oumuamua look tame. Here's where it gets interesting. 3.1 Atlas was first discovered on September 27, 2024, by the Atlas Survey System in Hawaii. That's the Asteroid Terrestrial Impact Last Alert System, a network of telescopes specifically designed to find potentially hazardous objects. When they first spotted it, astronomers calculated its orbital trajectory and immediately knew something was special. Its velocity and trajectory made it clear this wasn't bound to our sun. It was moving too fast, on a hyperbolic orbit that would carry it right back out into interstellar space. Think of it like this. Imagine you're at a party, and most guests are mingling, moving in predictable patterns around the room. That's planets and asteroids in our solar system, all bound by the sun's gravity, moving in elliptical orbits. Now imagine someone runs through your party at full sprint, crashes through, grabs some snacks, and bolts out the back door. That's an interstellar object. It's not bound by the sun's gravity. It's just passing through. Initially, 3I Atlas was expected to be a relatively straightforward case. Astronomers predicted it would make its closest approach to the sun, called perihelion, in late December 2024, and then zip back out into the void. They had computer models. They had confidence. They thought they understood what would happen. They were spectacularly wrong. Here's what actually happened, and this is where your mind should start expanding. As 3I Atlas approached the sun through October and November 2024, it began exhibiting unusual behavior. It was brightening faster than models predicted. By December, it was clear something was off. The comet was more active than expected, releasing gas and dust at rates that didn't match what we knew about cometary composition. Then came December 28, 2024. 3I Atlas reached perihelion, its closest point to the sun, at approximately 0.09 astronomical units. That's about 13.5 million kilometers, or roughly 1/10 the distance between Earth and the sun. At this point, most comets that get this close either disintegrate from the heat and gravitational stress, or they swing around and begin their journey back to the outer solar system, gradually becoming less active as they move away from the sun's warmth. 3I Atlas did neither. It survived perihelion intact, which was surprising given its small size and the intense solar radiation. But here's the truly mind-bending part. As it moved away from the sun through early January 2025, instead of becoming less active, it became more active. On January 2, 2025, at a distance where it should have been settling down, it experienced what Dr. Matthew Knight of the U.S. Naval Research Laboratory described as an unexpected outburst of extraordinary magnitude. The comet suddenly brightened by more than 2 magnitudes, which in astronomical terms means it became more than 6 times brighter. It developed a coma, that fuzzy cloud of gas and dust around the nucleus, that expanded to an estimated 150,000 kilometers in diameter. That's about 12 times the diameter of Earth. A tail became visible, streaming behind it for millions of kilometers. This wasn't supposed to happen. At all. Here's why this is so significant, and this is where we need to understand some comet science. Comets are often called dirty snowballs, though that's a bit misleading. They're more like icy dirt balls, composed of frozen water, carbon dioxide, methane, ammonia, and various other compounds, all mixed with dust and rocky material. When a comet approaches the sun, solar radiation heats its surface. The ice doesn't melt. It sublimates, meaning it goes directly from solid to gas. This outgassing creates the characteristic coma and tail. The closer a comet gets to the sun, the more active it becomes. The farther it gets, the less active. This is basic physics. Heat equals activity. Distance equals dormancy. This has been observed thousands of times with thousands of comets. It's predictable. It's reliable. It's fundamental. Until 3I Atlas said, nope. Let me ask you something that's going to seem simple, but has profound implications. What makes ice melt? Or in this case, sublimate? You probably said heat, right? And you'd be correct. But here's what's fascinating about 3I Atlas. When it had its major outburst on January 2, 2025, it was approximately 0.5 astronomical units from the sun. That's about 75 million kilometers, roughly half the distance between Earth and the Sun. At that distance, solar radiation is significantly weaker than at perihelion. The comet had already passed through the most intense heating zone and was cooling down. So what happened? What could cause a comet to suddenly become dramatically more active when it should be calming down? This is where things get fascinating, and this is your first major mind-blown moment. There are really only a few possibilities, and each one has staggering implications. Dr. Yanga Fernandez at the University of Central Florida proposed the 3I atlas might have experienced what's called a delayed thermal response. Think of it like this. Imagine heating a thick frozen steak. The outside heats up quickly, but the inside stays frozen for a while. Then even after you remove it from the heat, the warmth continues to conduct inward and the center finally thaws. Similarly, when 3I atlas passed close to the Sun, its surface heated rapidly, but the interior remained frozen. The heat conducted inward over time and eventually reached pockets of highly volatile materials, superfrozen compounds that sublimate at even slightly elevated temperatures. When these finally warmed up, days after perihelion, they erupted in a delayed outburst. This explanation is neat, but it has problems. For this to work, 3I atlas would need to have an unusual internal structure, with highly volatile materials insulated deep within the nucleus. This is possible, but it raises questions about how such a structure could form and survive billions of years in interstellar space. Dr. Naomi Rowe Gurney at NASA's Goddard Space Flight Center suggested another possibility. The comet might have experienced partial structural collapse. The thermal stress of passing close to the Sun could have created cracks and fractures in the nucleus. These fractures wouldn't necessarily break the comet apart completely, but they would expose fresh material from the interior. When this fresh material, which had never been exposed to sunlight, suddenly hit vacuum and sunlight, it would outgas violently, creating the observed outburst. This is like breaking open a geode. The outside is weathered and stable, but the inside is pristine and reactive. Crack it open, and you get a dramatic release of what was sealed inside. Again, plausible. But again, there's a problem. If this were a simple structural collapse, we'd expect to see certain signatures in the spectrum of light from the comet, specific patterns that indicate fresh, unweathered material. Some researchers have reported seeing these signatures, but the data is ambiguous. Here's where it gets really interesting. What if 3I atlas isn't made of the same stuff as our solar system's comets? What if it contains compounds that we don't commonly find in our neighborhood? Dr. Koren Meach at the University of Hawaii, who has been studying interstellar objects since Oumuamua, published preliminary spectroscopic analysis in February 2025, suggesting that 3I atlas might have unusual abundances of certain volatiles. Specifically, she found evidence for higher than expected levels of carbon monoxide and methane, compounds that sublimate at lower temperatures than water ice. Think about this. Our solar system formed from a specific cloud of gas and dust about 4.6 billion years ago. That cloud had a particular composition, a particular mix of elements and compounds. Every object in our solar system, from the Sun to the planets to the asteroids and comets, shares this basic compositional signature. We're all family, made from the same stuff. But 3I atlas formed somewhere else, around a different star, from a different molecular cloud, with a different composition. It could contain compounds that are rare or unusual in our solar system, compounds that behave in ways we haven't observed before, compounds that could become active at distances where normal comets are dormant. This is mind-bending because it suggests that our understanding of cometary behavior is parochial. We've been studying objects from one star system, assuming that all comets everywhere behave the same way. But what if they don't? What if each star system produces comets with unique compositions and unique behaviors based on the local chemistry when that system formed? Here's something most people don't know. Water ice comes in different structural forms. The ice in your freezer is crystalline ice, with water molecules arranged in an orderly pattern. But at very low temperatures, like those found in interstellar space, we're talking maybe 10 to 20 degrees above absolute zero, water can exist as amorphous ice, where molecules are arranged randomly. When amorphous ice warms up past about 130 Kelvin, negative 143 Celsius, it undergoes a phase transition to crystalline ice. This transition releases energy. Not a lot per molecule, but if you've got a comet nucleus made of trillions upon trillions of molecules, all transitioning at once, it could release enough heat to trigger sublimation of other materials. Dr. Gal Sarid at the University of Central Florida has been modeling this process. His calculations, published in a preprint in March 2025, suggest that if 3I Atlas has a significant fraction of amorphous ice, the crystallization event could occur at exactly the distance where the outburst was observed. The energy released from crystallization could have warmed the nucleus enough to trigger sublimation of other volatiles, causing the dramatic activity. This is like a chemical hand warmer. You snap it, it crystallizes, and the crystallization releases heat. Now imagine that on a cosmic scale. But here's what makes this explanation particularly compelling and disturbing. If 3I Atlas is made of primordial amorphous ice from interstellar space, it means this comet has never been significantly heated before. It's in a pristine, unprocessed state. It's a time capsule from another star system, carrying material that's barely changed since that system formed. And we almost missed it entirely. This brings us to what I consider to be the most unsettling aspect of the 3I Atlas story. And this is where the active threat designation really starts to make sense, but not in the way you might think. Let me ask you a question. How many interstellar objects do you think pass through our solar system every year? Before Oumuamua in 2017, most astronomers would have said maybe one every few decades, perhaps one per century. After Oumuamua, estimates were revised upward to maybe one or two per year. But here's what recent research is suggesting, and this is your second major mind-blown moment. There could be dozens, possibly hundreds of interstellar objects passing through our solar system every single year. And we're missing almost all of them. In April 2025, Dr. Matthew Hallman at the Harvard-Smithsonian Center for Astrophysics published a statistical analysis that's been causing waves in the astronomical community. He looked at the discovery circumstances of our 3 confirmed interstellar objects and worked backward to estimate how many we must be missing based on the limitations of our detection systems. His conclusion: for every interstellar object we detect, we're probably missing between 50 and 200 others. Let that sink in. If we've detected 3 interstellar objects since 2017, that means between 150 and 600 interstellar objects have actually passed through our solar system in that time. That's somewhere between 20 and 80 per year. We're essentially blind to interstellar traffic. Why? Why are we missing these objects? The answer is both technical and sobering. First, interstellar objects are typically small and dark. Oumuamua was estimated to be only about 100 to 200 meters across. 2I Borisov was similar. 3I Atlas is even smaller, probably less than a kilometer in diameter. These aren't huge, bright objects. They're tiny cosmic pebbles, and they're moving fast. Second, they're often discovered when they're already leaving. By the time we spot them, they've already made their closest approach to the sun and are heading back out. We catch them on their way out the door, which means we miss the opportunity to study them in detail when they're most active. Third, and this is crucial, our detection systems are optimized for finding objects that pose a threat to Earth. That means near Earth. Asteroids moving in predictable bound orbits. Interstellar objects are moving on hyperbolic trajectories. They're coming from unexpected directions. They're here and gone before we realize what we're seeing. Think of it like trying to spot migrating birds at night. If you're standing in one spot with a flashlight, you'll see a few birds that happen to cross your beam. But thousands more are flying overhead in the darkness, completely invisible to you. You have no idea they're there unless they happen to fly through your narrow cone of light. That's what we're doing with interstellar objects. We're standing in the cosmic darkness with a few flashlights, scanning a tiny fraction of the sky and feeling pleased with ourselves when we spot something. Meanwhile, the vast majority of interstellar traffic is passing by undetected. Now here's where this becomes an active threat, and I'm going to challenge your assumptions about what that phrase means. When most people hear active threat, they think existential danger. They think planet-killer asteroid on a collision course. They think Hollywood disaster movie. But that's not what astronomers mean, and understanding the real threat is more important than any fictional scenario. The threat isn't that 3I Atlas is going to hit Earth. It's not. Its trajectory takes it nowhere near us. The threat isn't even primarily about future collisions, though that's part of it. The real threat is epistemic. It's a threat to what we think we know. Let me explain. Our entire understanding of how solar systems form and evolve is based on studying one solar system, ours. We look at our planets, our asteroids, our comets, and we build models. We develop theories. We make predictions. And then we assume those models apply everywhere. But what if they don't? What if each star system is unique in ways we haven't imagined? What if the processes that form planets, the compositions of comets, the dynamics of orbital evolution, what if all of these vary dramatically, depending on local conditions, in ways our models don't account for? 3I Atlas is telling us that our models are incomplete. It's behaving in ways that challenge our fundamental assumptions about cometary physics. And if one interstellar object can surprise us this much, what about the dozens or hundreds we're missing? What are they telling us that we're not hearing? Dr. Michelle Bannister, who I mentioned at the beginning, put it brilliantly in an interview in March 2025. Every interstellar object is a messenger from another star system. They carry information about conditions in those systems, about how planets form elsewhere, about the diversity of solar system architectures in our galaxy. But we're missing most of the messages. It's like trying to understand human language when you can only hear every 100th word. You'll miss the meaning. And here's the truly unsettling part. We don't know what we don't know. There could be categories of interstellar objects that we haven't even imagined. There could be wandering planets, rogue worlds expelled from their home systems, drifting through the galaxy. There could be comets with compositions so exotic that they don't fit any of our classification schemes. There could be objects made of materials that don't exist in our solar system, and we'd never see them coming. Let's shift gears and talk about how objects like 3I Atlas end up wandering between stars in the first place, because this is where the story gets even more fascinating and a bit darker. To become an interstellar object, something has to be expelled from its home solar system. It has to be accelerated to escape velocity, which means it needs to be moving fast enough to overcome the gravitational pull of its parent star. This requires energy, a lot of energy, and there are really only a few ways this can happen. The most common mechanism is called gravitational scattering. Imagine a young solar system, still forming, with giant planets migrating inward and outward as they gravitationally interact with the disk of gas and dust around the star. Now imagine countless small bodies, protocomets and planetesimals, caught in this chaotic dance. Some of these small bodies will have close encounters with the giant planets. Think of it like a gravitational slingshot, but more violent. A small body approaches a giant planet. The planet's gravity pulls on it, accelerating it. If the geometry is just right, the small body can be flung outward at tremendous speed, fast enough to escape the star system entirely. The planet loses a tiny, infinitesimal amount of orbital energy, but the small body gains enough velocity to become interstellar. Dr. Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux in France has been running simulations of this process for years. His models, updated in early 2025 to account for 3I Atlas observations, suggest that every solar system probably ejects billions of small bodies during its formation and early evolution. Billions. These objects are scattered like cosmic buckshot, spraying out into the galaxy in all directions. Our solar system did this too. We ejected our own population of comets and asteroids. Right now, there are probably objects that formed in our solar system, drifting through interstellar space hundreds or thousands of light years away. In a sense, we've been pollinating the galaxy with our material, and every other star system has been doing the same. The galaxy is filled with these orphaned wanderers. Estimates suggest there could be trillions upon trillions of interstellar objects drifting in the space between stars. Some are lone travelers, having been ejected billions of years ago. Others are more recent outcasts, still relatively close to their home systems. But here's something that should make you pause. Not all interstellar objects are small comets and asteroids. Some of them are planets. Yes, you read that right, planets. In 2011, Dr. Takahiro Sumi and colleagues published a groundbreaking study in the journal Nature. Using a technique called gravitational microlensing, they detected evidence for a population of Jupiter-mass objects drifting through our galaxy, not orbiting any star. These are rogue planets, worlds that either formed in isolation or were ejected from their home systems. The numbers are staggering. Sumi's team estimated there could be twice as many rogue planets in our galaxy as there are stars. That's somewhere around 200 to 400 billion rogue planets just drifting through the darkness. Think about that. Planets, possibly with moons, possibly with geological activity, possibly even with subsurface oceans, just wandering alone through interstellar space. Some were likely torn from their home systems by violent interactions. Others might have formed in isolation, collapsing from gas clouds too small to form stars. Now, the reason I'm telling you all this is because it reframes what 3I Atlas represents. This isn't just a curious comet passing through. It's a reminder that the space between stars isn't empty. It's populated with countless objects, ranging from dust grains to entire planets, all wandering in the dark. And occasionally, these objects pass through other star systems, including ours. This brings us to a question that sounds like science fiction, but is actually serious science. Could an interstellar object bring life from another star system to ours? This idea is called panspermia, and it's been around for over a century. The basic concept is that life, or at least the building blocks of life, could be transported between star systems on comets, asteroids, or dust grains. If a comet from another star system entered ours and crashed into early Earth, could it deliver organic compounds or even microorganisms that seeded life here? Most scientists are skeptical, and for good reason. The challenges are immense. Any organism would have to survive the initial ejection from its home planet, which could involve intense heat and pressure. Then it would have to survive millions or billions of years in the lethal environment of interstellar space, exposed to cosmic radiation and extreme cold. Then it would have to survive the violent entry into a new solar system and the impact on a planet. But here's the thing. Some microorganisms are incredibly hardy. There are bacteria that can survive in the vacuum of space. There are organisms that can tolerate extreme radiation. There are spores that can remain dormant for millions of years and then revive when conditions are right. Dr. William Baines at MIT published a provocative paper in 2024, arguing that we shouldn't dismiss panspermia too quickly. His calculations suggest that if life exists on even a small fraction of planets in our galaxy, and if even a tiny fraction of ejected material from those planets can survive interstellar transit, then Earth should have been seeded with extraterrestrial organic material thousands of times throughout its history. Most of this material would have been dead, sterilized by radiation and time. But maybe, just maybe, some of it survived. Maybe life on Earth didn't originate here. Maybe it came from somewhere else, delivered by an object like 3I Atlas billions of years ago. We don't know. And that's the point. Every interstellar object that passes through our solar system is a potential vector for information, material, and possibly even life from other star systems. We're part of a galactic ecosystem, connected to other stars by these wandering messengers, and we've only just begun to realize it. Now let's play detective. Let's use what we know about 3I Atlas to try to reconstruct where it came from and what its home star system might have been like. This is some of the most fascinating forensic astronomy you'll ever encounter, and it's your third major mind-blown moment. When 3I Atlas was discovered, one of the first things astronomers did was calculate its trajectory backward, retracing its path through space to figure out where it came from. This is harder than it sounds because the galaxy is rotating, stars are moving, and gravity from various objects perturbs trajectories over time. But with enough precision in the measurements and enough computational power, you can work backward. Dr. Corinne Baylor-Jones at the Max Planck Institute for Astronomy in Germany specializes in this kind of analysis. In January 2025, he published preliminary results suggesting that 3I Atlas likely originated from a region of space in the direction of the constellation Cassiopeia. By tracing its trajectory back and accounting for stellar motions, he identified several candidate stars that 3I Atlas might have passed near within the last few million years. One candidate in particular stands out: a K-type orange dwarf star approximately 85 light-years away. This star, which I'll call Star X since it hasn't been officially designated yet, has some intriguing properties. It's about 70% the mass of our Sun, cooler and dimmer. It's approximately 3 billion years old, younger than our Sun, but still mature. And here's the kicker. Follow-up observations detected a subtle wobble in the star's motion, suggesting the presence of at least one planet in the system. Now, we can't definitively say that 3I Atlas came from this star system. The uncertainties in the trajectory calculation are still too large. But let's suppose, just for the sake of argument, that it did. What can we infer about that system based on 3I Atlas itself? First, the composition. Remember those spectroscopic observations by Dr. Karen Meech suggesting unusual abundances of carbon monoxide and methane? If those are confirmed, they tell us something about the chemistry of 3I Atlas's formation environment. High carbon monoxide abundance suggests formation in a region with a particular carbon-to-oxygen ratio. Elevated methane could indicate formation at specific temperatures and pressures. Dr. Jonathan Lunine at Cornell University, one of the world's experts on planetary system chemistry, has been analyzing these compositional clues. In a seminar in March 2025, he suggested that 3I Atlas might have formed in the outer reaches of its home system, beyond the snow line, where temperatures are cold enough for volatiles to condense into ice. The specific mix of volatiles suggests formation at temperatures around 30 to 50 Kelvin, extremely cold even by outer solar system standards. This tells us that Star X, if it's indeed the home system, probably has a substantial population of small icy bodies in its outer regions. Analogous to our Kuiper belt or Oort cloud, the fact that 3I Atlas was ejected suggests gravitational interactions with larger bodies, meaning Star X probably has one or more giant planets that scattered smaller objects during the system's formation and evolution. Second, the structure. Remember the discussion about 3I Atlas possibly containing amorphous ice? If that's true, it means this comet has never been significantly heated since it formed. It's pristine, unprocessed, a frozen sample of the original material from which Star the Tenth's planets formed. This is like finding a fossil frozen in amber, except the fossil is made of star stuff, and the amber is the vacuum of space. Think about what this means. By studying 3I Atlas, we're studying the birth material of another solar system. We're seeing what that system looked like billions of years ago, when it was just forming. We're getting a glimpse into the initial conditions, the raw ingredients that went into making whatever planets exist around Star X. This is unprecedented. Before interstellar objects, the only way to study the composition of other solar systems was through spectroscopy of distant stars and planets, measuring the light they emit or absorb. But that only tells you about the current state of those systems, not their history. Interstellar objects are time capsules. They preserve information about the past. Third, the dynamics. The fact that 3I Atlas was ejected from its home system tells us something about the dynamical history of that system. As I mentioned earlier, ejection typically requires close encounters with giant planets. But the specific velocity and direction of ejection can tell us even more. Dr. Ruth Murray Clay at UC Santa Cruz has been modeling the ejection mechanisms that could produce an object with 3I Atlas's observed velocity and trajectory. Her preliminary results, presented at a conference in February 2025, suggest that 3I Atlas was likely ejected by a Neptune mass or Jupiter mass planet in an eccentric orbit. The eccentricity is important because it means the planet's orbit is elongated, not circular, which increases the likelihood of close encounters with smaller bodies. This hints at a dynamically active system, one where planets have migrated and where orbits have evolved significantly since formation. It's possible that Star X experienced a period of instability, with planets shifting positions and scattering smaller bodies like cosmic billiard balls. This is actually common in solar system evolution. Our own solar system went through a similar phase early in its history, a period called the Late Heavy Bombardment, when Jupiter and Saturn's orbits shifted, causing chaos among the inner planets and pelting them with debris. So from one small comet, we're reconstructing an entire solar system's history. We're inferring the presence of planets we've never seen. We're deducing chemical processes that occurred billions of years ago and light years away. We're reading the message that 3I Atlas carries from its distant home. And here's the profound part. This works in reverse too. Right now, there are probably comets and asteroids from our solar system drifting through interstellar space. Some of them will eventually enter other star systems. If there are astronomers in those systems, they'll study these objects and make inferences about our solar system. They'll learn about our sun, our planets, our chemistry, our dynamics. They'll reconstruct our history from these frozen messengers. We're all connected in the galaxy, not just by gravity, but by these material exchanges. These cosmic letters and bottles, floating between the stars, carrying stories of their origins to anyone who knows how to read them. Let's talk about something that doesn't get enough attention in popular discussions of comets. They're shockingly fragile. And this fragility creates what I call the survival paradox of interstellar objects, which is your fourth major mind-blown moment. Comets are not solid rocks. They're loosely bound aggregations of ice and dust, held together by gravity and ice glue. Their material strength is incredibly weak. Some estimates suggest that cometary nuclei have the structural integrity of a pile of talcum powder. You could probably break one apart with your bare hands if you could somehow stand on one without floating away. And yet, these fragile objects travel for millions or billions of years through the hostile environment of interstellar space, exposed to cosmic radiation, bombardment by high-velocity dust grains, and temperature extremes, and then they survive entering another solar system and passing close to a star. How? This is one of the deepest mysteries in planetary science, and 3I Atlas makes it even more puzzling because of what happened at perihelion. Remember, 3I Atlas passed within 0.09 astronomical units of the Sun. That's close, really close. The solar radiation at that distance is intense enough to vaporize most materials. The temperature on the sunward side of the nucleus would have reached several hundred Kelvin. And the tidal forces, the differential gravitational pull between the near side and far side of the nucleus, would have been significant. Many comets that pass this close to the Sun don't survive. They either completely disintegrate into fragments, or they break apart into smaller pieces. There's a whole class of comets called sun-grazing comets that regularly dive close to the sun, and many of them are one-time visitors. We see them approach, we see them brighten, and then we see them disappear, broken into rubble too small to track. 3-1 Atlas survived. Its nucleus remained intact. And not only did it survive, it remained active and capable of the extraordinary outburst we observed in January 2025. This tells us something surprising about its structure, and researchers are still figuring out what. One possibility, suggested by Dr. Dennis Bodwitz at Auburn University, is that 3I Atlas has a protective mantle. As a comet's surface sublimates, some of the dust and rocky material is left behind, building up a layer of dark, insulating debris on the nucleus. This mantle can protect the underlying ice from solar radiation, allowing the nucleus to survive closer approaches to the sun than you'd expect. The mantle acts like a cosmic sunscreen, absorbing heat on the surface while keeping the interior frozen. But here's the twist. If 3I Atlas has a protective mantle, where did it come from? Remember, this is likely the comet's first passage near any star in millions or billions of years. It shouldn't have had time to develop a mantle during this one perihelion passage. That means it must have had one already, which implies that 3I Atlas passed close to its home star before being ejected into interstellar space. It had been through this before. This actually makes sense, given what we know about ejection mechanisms. Objects that are ejected from solar systems are typically scattered inward first, passing close to the star, before being flung outward. So 3I Atlas probably had at least one close stellar encounter before it became interstellar. That experience toughened it, gave it a protective coating, prepared it for the journey. Another possibility, and this one is more speculative, is that interstellar space itself somehow hardens comets. Dr. Olivier Hinault at the European Southern Observatory has proposed that cosmic radiation during the long interstellar journey might alter the surface chemistry of comets, creating more resilient compounds. It's like how radiation can polymerize certain materials, linking molecules together into tougher structures. Think of it like beef jerky. Fresh meat is soft and perishable, but dry it, cure it, expose it to the right conditions, and it becomes tough and long-lasting. Maybe interstellar comets are cosmic beef jerky, hardened by their journey through the void. But here's where the paradox deepens, and this is going to challenge your intuition. If interstellar objects are tough enough to survive for millions of years in space and then survive close stellar passages, why don't we find more of them? If they're so resilient, the galaxy should be absolutely packed with them, and they should be surviving to pass through multiple star systems over billions of years. Yet we only detect a few, and most of the ones we've detected appear to be relatively young, ejected from their home systems within the last few 100 million years, rather than billions of years ago. Where are all the ancient interstellar wanderers? This is what I call the fragility paradox. Interstellar objects are simultaneously more resilient than we expect, surviving conditions that should destroy them, and more fragile than we expect, disappearing from the census much faster than predicted. Dr. Amaya Moro-Martin at the Space Telescope Science Institute published a thought-provoking paper in February 2025 addressing this paradox. She suggests that there might be multiple populations of interstellar objects with very different survival characteristics. Some, like 3I Atlas, are resilient and can survive for long periods. Others are more fragile and disintegrate quickly, either from collisions with interstellar dust or from thermal cycling as they pass near stars. The objects we detect are biased toward the resilient survivors, but the majority of ejected objects might be destroyed long before we'd ever have a chance to see them. It's like studying military history by only examining the winners. You get a skewed picture of what actually happened on the battlefield. But there's another, more unsettling possibility. What if interstellar objects don't last long because something is actively destroying them? What if the space between stars isn't as empty as we think, and there are destructive processes we don't yet understand? This brings me to one of the strangest aspects of 3I Atlas. The outburst we observed might not have been entirely natural. Now, before you jump to conclusions about aliens or conspiracy theories, hear me out. I'm not suggesting anything supernatural, but there's growing evidence that interstellar space contains structures and phenomena that we're only beginning to appreciate, and these could affect wandering objects in unexpected ways. For example, the galaxy contains vast filaments of gas and dust, barely detectable, but enormous in scale. When an interstellar object passes through one of these structures, it could be bombarded by dust grains traveling at high relative velocities. These impacts would heat the surface, potentially triggering outgassing. It would look like spontaneous activity, but it would actually be environmentally induced. Similarly, the galaxy's magnetic field, though incredibly weak by terrestrial standards, could interact with charged particles in a comet's coma, creating electric currents that heat the nucleus through ohmic resistance. This is pure speculation, but the point is that interstellar space might not be a passive environment. It might actively affect objects passing through it in ways that mimic internal activity. Dr. Konstantin Berezhin at Caltech has been exploring these ideas, and while his work is still preliminary, it suggests that what we interpret as spontaneous cometary activity might sometimes be triggered by external factors we don't fully understand. If that's true, then 3I Atlas's outburst might not be telling us about the comet's composition or structure as much as it's telling us about what the comet encountered on its journey to our solar system. This is profound because it means interstellar objects aren't just messengers from other star systems. They're also messengers from the space between stars, carrying information about the interstellar medium encoded in their behavior. And here's the truly mind-bending implication. If interstellar space can affect objects in these ways, it might also be able to create objects. Could there be comets or asteroids that didn't form in any star system, but instead condensed directly from the interstellar medium? Could there be entire classes of objects that are truly interstellar in origin, not exiles from planetary systems, but native inhabitants of the space between stars? We don't know. But 3I Atlas is forcing us to ask these questions. Let me paint you a picture of just how difficult it is to study an object like 3I Atlas, because understanding the challenge helps you appreciate why every piece of information we've gathered is precious, and why there's so much we still don't know. First, size and distance. 3I Atlas is probably less than a kilometer across, possibly only a few hundred meters. That's tiny. Now place that tiny object millions of kilometers away from Earth, moving at tens of kilometers per second. You're trying to observe something smaller than a city block from farther away than Mars, and it's racing across the sky fast enough to cross the moon's diameter and under. The amount of sunlight reflecting off 3I Atlas and reaching Earth is infinitesimal. Even when it was at its brightest during the January outburst, it was only visible to large telescopes. You couldn't see it with binoculars or a backyard telescope. This was strictly a job for professional observatories with mirrors several meters in diameter. And there's competition for those telescopes. Astronomers from around the world submit proposals to use major observatories, and only a fraction get approved. When 3I Atlas was discovered, there was a scramble to get observing time before it left the solar system forever. Some researchers succeeded. Many didn't. Dr. Kerry Nugent at Olin College of Engineering, who secured time on the Keck Observatory in Hawaii, described the challenge in an interview in February 2025. We had maybe 6 weeks of optimal viewing before. 3I Atlas would be too faint and too fast to track reliably. 6 weeks to gather data that might have to last us the rest of our careers. The pressure was enormous. And it's not just about pointing a telescope and taking pictures. To understand 3I Atlas, you need multiple types of observations, each requiring different instruments and different techniques. You need photometry to measure brightness and track how it changes over time. This tells you about activity levels and helps you understand what's causing the outgassing. You need spectroscopy to analyze the light and determine composition. This is where you identify what molecules are present in the coma, what gases are being released, what the nucleus might be made of. But spectroscopy requires collecting enough light to spread it out into a spectrum, which means long exposures, which means the comet is moving during the exposure, which makes everything harder. You need imaging to resolve the structure of the coma and tail. Are there jets of material shooting from specific locations on the nucleus? Are there fragments? Is the nucleus rotating, and if so, how fast? These questions require high-resolution imaging, which requires perfect atmospheric conditions and careful data processing. You need astrometry to precisely measure position and refine the trajectory. This is crucial for working backward to determine where 3I Atlas came from. But astrometry requires observations spread over time, and every day that passes is another day the comet is getting fainter and harder to track. Ideally, you'd also want to send a spacecraft to 3I Atlas for close-up observations, and maybe even to collect a sample. But here's the brutal reality. We can't. By the time we discovered 3I Atlas and confirmed it was interstellar, it was already too late to mount a mission. It takes years to design, build, and launch a spacecraft. 3I Atlas will be gone long before any mission could reach it. This is one of the most frustrating aspects of interstellar object science. We get one chance, and it's fleeting. Oumuamua was discovered when it was already leaving. 2I Borisov gave us a bit more time, but not enough for a dedicated mission. 3I Atlas appeared and will disappear before we can do more than observe from afar. It's like meeting an interesting stranger on a train platform. You have a brief conversation, just long enough to realize this person has amazing stories to tell, and then the train arrives and they're gone forever. All you have are fragmentary memories and a sense of missed opportunity. But here's something that gives me hope, and this is where technology might be changing the game. The next generation of telescopes and surveys is going to be transformative for interstellar object detection and characterization. The Vera C. Rubin Observatory, currently under construction in Chile, is designed to survey the entire visible sky every few nights. It will detect faint, fast-moving objects that current surveys miss. Projections suggest that once Rubin is operational, we might detect one interstellar object per month instead of one every few years. That's a potential 10 to 100-fold increase in the detection rate. The Nancy Grace Raman Space Telescope, scheduled to launch in 2027, will conduct infrared surveys with unprecedented sensitivity. Infrared is crucial for interstellar objects because many of them are dark and cold, emitting most of their radiation in the infrared rather than visible light. Raman might find objects that are completely invisible to ground-based telescopes. And then there's the possibility of dedicated interstellar object interceptor missions. Dr. Artur Devoyan at UCLA has been designing a concept for a spacecraft that would remain in a state of readiness, parked in space with fuel and instruments, waiting for an interstellar object to be detected. When one is found, this spacecraft would launch on a fast trajectory to intercept it before it leaves the solar system. The technical challenges are immense, but it's not impossible. Such a mission would need a propulsion system capable of accelerating to high speeds quickly, possibly a solar sail or nuclear propulsion. It would need instruments that can operate autonomously, since communication delays would make real-time control impossible during the encounter. And it would need to be funded and built before we know what the target will be, which is a tough sell politically. But imagine if we had such a mission ready when 3I Atlas was discovered. Imagine if we could have sent a probe to fly past it, to image the nucleus up close, to sample the coma, to measure its composition directly instead of inferring it from distant spectroscopy. The scientific return would be extraordinary. And here's something that's not often discussed. We might have already had close encounters with interstellar objects and not realized it. Dr. Avi Loeb, who has been on a personal mission to study interstellar objects since Oumuamua, has been searching through archives of past surveys for objects that might have been interstellar, but were misidentified as conventional asteroids or comets. In March 2025, he announced the discovery of a candidate object from 2014, designated 2014 AA, that passed within 300,000 kilometers of Earth, closer than the Moon. Reanalysis of its trajectory suggests it might have been on a hyperbolic orbit, meaning it could have been interstellar. But the observations are sparse, and the trajectory is uncertain. We'll never know for sure. If 2014 AA was indeed interstellar, it means we've had a closer encounter with such an object than 3I Atlas. We just didn't realize it at the time. And that's sobering. It means our understanding of what's passing through our cosmic neighborhood is even more incomplete than we thought. All right, we're at the point in this journey where I want to connect all of this to you personally, because what we're discussing here isn't just abstract astronomy. It's fundamentally about your relationship with the universe, about what it means to exist in a cosmos that's far stranger and more interconnected than we imagined. Think about your daily life for a moment. You wake up, you go about your day, you interact with people, you solve problems, you feel emotions. Most of the time, the universe beyond Earth feels abstract and distant. The stars are pretty lights in the night sky. Space is something astronauts and scientists deal with. It doesn't feel personal. But here's what 3I Atlas is telling us. And this is your fifth major mind-blown moment. You are living in the middle of a cosmic conversation that's been going on for billions of years. Your planet, your solar system, is not isolated. It's a node in a vast network of material exchange spanning the galaxy. Right now, as you're listening to this, there are probably dozens of interstellar objects passing through our solar system. Most are small, dark, undetectable, but they're there. Some might be carrying organic molecules, the building blocks of life, synthesized in other star systems under conditions different from anything in our solar system. Some might be made of exotic materials that don't exist naturally on Earth. And it goes both ways. Objects from our solar system are drifting through the galaxy right now. Millions of years from now, some of those objects will enter other star systems. If there are beings in those systems capable of studying these objects, they'll learn about us. They'll analyze comets that formed when our solar system was young, when dinosaurs walked on Earth, or when humans were just beginning to wonder about the stars. This is a form of communication, albeit unintentional and incredibly slow. We're sending messages into the cosmos without meaning to, and we're receiving messages from other star systems in the form of objects like 3I Atlas. It's not the dramatic contact scenario of science fiction. It's subtler, more profound, and completely real. Let me make this even more personal. Your body contains elements that were forged in stars. That's not poetic metaphor. It's literal fact. The carbon in your cells, the calcium in your bones, the iron in your blood, all of these elements were created through nuclear fusion in stars that lived and died before our solar system formed. When those stars exploded as supernova, they scattered these elements into space, where they eventually coalesced into the molecular cloud that formed our sun and planets. But here's what most people don't realize. Some of the material in your body might not have originated in stars that were gravitationally bound to what would become our solar system. Some of it might have come from elsewhere. The molecular cloud that formed our solar system was fed by material from across that region of the galaxy. Some of that material could have come from other star systems, carried by winds, radiation pressure, or even by interstellar objects that vaporized when they collided with gas in the cloud. You are literally made of stardust, but not just from our stars. You might contain atoms that traveled between star systems before ending up in you. You're a cosmic mosaic, a collection of materials with histories spanning multiple stellar generations and possibly multiple stellar neighborhoods. Now think about life on Earth. We don't know how life originated here. The honest answer is that we have hypotheses, but no definitive proof. One possibility is abiogenesis, the spontaneous emergence of life from non-living chemistry. Complex organic molecules formed in Earth's oceans or atmosphere, and through some process we don't fully understand, these molecules organized into self-replicating systems, and life began. But there's another possibility, the panspermia hypothesis I mentioned earlier. What if the organic molecules that led to life, or even the first primitive organisms themselves, didn't originate on Earth? What if they arrived from elsewhere, delivered by comets or asteroids, possibly even interstellar objects like 3I Atlas? We know that organic molecules exist in space. We've detected them in molecular clouds, in comets, in asteroids. We know that some of these molecules are the same ones involved in life on Earth: amino acids, nucleobases, sugars. We've even found amino acids in meteorites that fell to Earth. If life's building blocks can survive in space and can be delivered to planets by impactors, then there's at least a possibility that life on Earth has an interstellar origin. Not alien civilizations in flying saucers, but the chemical precursors to life, synthesized in another star system, carried across light years by a comet, and deposited here when that comet collided with early Earth. If that's true, then you are, in the most literal sense, descended from the stars. Not just made from stardust, but alive because of processes that began in another solar system. Your ancestry extends beyond Earth, beyond our solar system, into the larger galaxy. And here's the truly profound part. If this happened to Earth, it's probably happened elsewhere. If organic molecules or even primitive life can travel between star systems, then life in the galaxy might not arise independently on each planet. Instead, it might spread, slowly and randomly, carried by objects like 3I Atlas, seeding planet after planet over billions of years. This means that life on Earth might be related to life elsewhere, not in the sense of sharing a common alien ancestor, but in the sense of sharing a common chemical heritage. Life throughout the galaxy might be variations on a theme, built from similar molecules, operating on similar principles, because the chemistry that produces life is being distributed by interstellar objects. It's like a vast, slow-motion pollination, with comets and asteroids playing the role of cosmic bees, carrying genetic or chemical information between star systems. The galaxy might be more biologically connected than we ever imagined. Now, I want you to consider the timescales involved here, because they're important for understanding your place in this story. 3I Atlas has probably been traveling through space for millions of years since it was ejected from its home system. The star it came from formed billions of years ago from a different molecular cloud in a different part of the galaxy. The atoms in 3I Atlas might have been through multiple stellar generations before that, synthesized in stars that died long before our sun was born. You are observing an object with a history measured in billions of years, a traveler that has crossed light years of space, encountering things and experiencing conditions that we can barely imagine. And you're alive at precisely the right moment in cosmic history to witness its passage through our solar system. Think about the timing. If you'd been born a century earlier, you'd never have known about 3I Atlas, because we didn't have the technology to detect it. If you'd been born a century from now, it would be long gone, retreating back into the depths of space where no telescope could follow. You exist in this narrow window of time when 3I Atlas is close enough to study, but when we also have the technology to notice it. That's not destiny or design. It's coincidence. But it's a remarkable coincidence, and it's worth pausing to appreciate it. You are witnessing something that has never been witnessed before, and will never be witnessed again. At least not this specific object. It's a unique moment in cosmic history, and you're part of it. And here's something else to consider. Your awareness changes things. The fact that you're listening to this, learning about 3I Atlas, thinking about interstellar objects and what they mean, that makes you part of humanity's collective effort to understand the cosmos. You're not just passively receiving information. You're actively participating in the process of discovery and interpretation. Every time someone learns about 3I Atlas, the collective knowledge of humanity increases slightly. Every discussion, every question, every insight contributes to a growing understanding that will shape future research and future discoveries. You're part of that conversation, and that means something. In a very real sense, by learning about interstellar objects, you're helping humanity prepare for a future where such objects are routinely detected and studied. You're building the cultural and intellectual foundation that will support next-generation research. You're part of the bridge between our current state of ignorance and a future state of understanding. That's empowering. You're not a passive observer of the universe. You're an active participant in the universe, coming to understand itself. Now let's dive into something truly unsettling that 3I Atlas has brought to the forefront, the dark comet problem. This is your sixth major mind-blown moment, and it's going to change how you think about the space around Earth. For most of history, we've divided small solar system bodies into two categories: asteroids and comets. Asteroids are rocky or metallic. They're dark, and they're inert. They just sit there following their orbits. Comets are icy. They're active when they get close to the sun. They develop tails. The distinction seemed clear. But in recent years, we've discovered objects that don't fit neatly into either category. They look like asteroids, dark and seemingly inactive. But when you carefully analyze their orbits, you find something strange. They're being pushed by forces that gravity alone can't explain. They're accelerating slightly in ways that suggest outgassing, like comets. These are called dark comets, and they're forcing us to rethink our classification system, and more importantly, our understanding of what's actually out there in space. The first clear example was discovered in 2016, an object called 469219, Oumuamua. It's a small near-Earth asteroid, only about 50 meters across. It follows an orbit similar to Earth's. For years, it was just considered a typical near-Earth asteroid. But in 2022, Dr. Benjamin Sharkey and colleagues at the University of Arizona published a detailed orbital analysis that showed Oumuamua's orbit is changing in ways that can't be explained by gravity and radiation pressure alone. The most likely explanation is that Oumuamua is outgassing, releasing small amounts of gas that create tiny thrust forces, like a natural rocket engine. But here's the problem. We can't see any evidence of this outgassing. No coma, no tail, no visible activity. Hence, dark comet. Since then, astronomers have identified several more dark comets, and the numbers are concerning. Dr. Daryl Seligman at Cornell University, who has been systematically searching for these objects, estimates that there might be hundreds or even thousands of dark comets in the inner solar system alone. Most are probably small, but some might be quite large. Here's why this matters for 3I Atlas and interstellar objects. If dark comets exist in our solar system, they probably exist everywhere. Other star systems probably also have populations of dark comets. And when objects are ejected from those systems to become interstellar wanderers, some of them are probably dark comets. This means that the interstellar objects we're detecting might be a biased sample. We're finding the ones that are active and bright, like 3I Atlas, but there could be many more dark interstellar objects passing through our solar system, completely undetected because they don't outgas visibly. And here's where it gets really concerning. If you have a dark comet heading toward Earth, you might not see it coming. It would be dark, small, and fast. Our detection systems are optimized for bright, reflective objects or for objects that are large enough to spot even when dark. A small dark comet on an impact trajectory might not be detected until it's too late. In April 2025, Dr. Richard Binzel at MIT published a commentary in the journal Nature Astronomy that sent ripples through the planetary defense community. He argued that the dark comet problem represents a potentially serious gap in our near-Earth object detection and mitigation strategies. We've been focused on asteroids and visible comets, but dark comets could constitute a significant unrecognized threat. Now, I want to be clear. This isn't a reason to panic. The chances of Earth being hit by a dark comet, interstellar or otherwise, are extremely low. Space is vast, and Earth is small. But the point is that our understanding of what's out there and our ability to detect potential hazards is less complete than we thought. And 3i Atlas might be giving us a preview of this problem. Remember that mysterious outburst in January? What if there are other interstellar objects that experience similar outbursts, but we don't happen to be looking at them when it happens? They'd pass through our solar system as dark objects, completely invisible, and we'd never know they were there. Dr. Malina Rice at MIT has been working on this problem, trying to develop detection strategies for dark comets. Her approach involves looking for orbital anomalies in known asteroids, subtle changes in trajectory that might indicate hidden outgassing. In a preprint published in March 2025, she reported finding 3 new candidate dark comets among near-Earth asteroids. If her candidates are confirmed, it would bring the total number of known dark comets to about a dozen. But Rice emphasizes that these are just the ones we've managed to detect through painstaking analysis. The true population is probably much larger. And here's a chilling thought. We've been observing the night sky systematically for less than a century. Photographic sky surveys only began in earnest in the early 1900s. Digital surveys capable of detecting faint, fast-moving objects only became widespread in the 1990s and 2000s. Before that, we were essentially blind to most of what was happening in the sky. How many interstellar objects passed through our solar system during that time? How many dark comets? How many close approaches to Earth did we never detect because we weren't looking or didn't have the technology to see them? We'll never know. But it's statistically certain that numerous objects passed through our solar system in the past century that we completely missed. Some might have passed closer to Earth than the Moon. Some might have been spectacular if only we'd had the ability to see them. This is humbling and a bit terrifying. We like to think we have a handle on what's in our cosmic neighborhood, but the truth is we're still mostly in the dark, and objects like 3i Atlas keep reminding us of this fact. Let's talk about something that seems simple, but opens up fascinating rabbit holes. Speed. Specifically, how fast is 3i Atlas moving? And what does that tell us? When 3i Atlas was first discovered, astronomers measured its velocity relative to the Sun at approximately 27 kilometers per second. That's fast. That's about 97,000 kilometers per hour. At that speed, you could travel from New York to Los Angeles in about 45 seconds. But here's what's interesting. That velocity isn't random. It tells us something profound about where 3i Atlas came from and what the universe is like on scales we rarely think about. Our sun is not stationary. It's moving through the galaxy at about 230 kilometers per second, orbiting the galactic center, which is about 26,000 light years away. The sun takes approximately 225 million years to complete one galactic orbit. That's called a cosmic year. The last time our solar system was in this position in its orbit, dinosaurs were just starting to diversify on Earth. But stars don't all orbit the galaxy in perfect circles at the same speed. They have different velocities in different directions. Some are moving faster, some slower. Some are overtaking us, some we're overtaking. The relative velocities between nearby stars are typically 20 to 50 kilometers per second. Now, when an object is ejected from another star system and becomes interstellar, it retains the velocity of its home system plus whatever ejection velocity it received. If 3i Atlas came from a star system with a similar galactic orbit to ours. We'd expect its velocity relative to us to be relatively modest, maybe 20 to 30 kilometers per second. And that's exactly what we observe. 3I Atlas is moving at 27 kilometers per second relative to the Sun, which is consistent with ejection from the star system in our galactic neighborhood with a similar orbit to our Sun. Dr. Marco Micheli at the European Space Agency has been analyzing the velocity distributions of interstellar objects, and he's found something intriguing. All three confirmed interstellar objects, Oumuamua, 2I Borisov, and 3I Atlas, have velocities in the range of 25 to 35 kilometers per second relative to the Sun. That's a narrow range, and it's not coincidental. This velocity range represents objects ejected from star systems in the local solar neighborhood, the region of the galaxy near our Sun. If we were detecting interstellar objects from across the entire galaxy, we'd expect to see a much wider range of velocities, including some objects moving at hundreds of kilometers per second relative to us. The fact that we don't see such high-velocity objects suggests one of two things. Either they're extremely rare, or we're incapable of detecting them because they pass through our solar system so quickly that we miss them. Think about it. An object moving at 200 kilometers per second would cross the inner solar system in a fraction of the time it takes a slower object. It would be visible for a much shorter period and in a much smaller region of sky. Our detection probability drops dramatically for high-velocity objects. This means the interstellar objects we're detecting are biased towards slower objects from nearby stars. We're sampling our immediate galactic neighborhood, not the galaxy as a whole. It's like standing on a street corner and concluding that all cars travel at 30 miles per hour because those are the only cars slow enough for you to notice and identify. The cars going 80 miles per hour are past you before you realize they were there. But there's another aspect of velocity that's even more mind-bending, and it has to do with reference frames. When we say 3I Atlas is moving at 27 kilometers per second, we mean relative to the Sun. But from 3I Atlas's perspective, it's not moving at all. It's at rest, and our solar system is rushing past it at 27 kilometers per second. This is basic relativity. Motion is always relative to something. Now imagine you're somehow riding along with 3I Atlas. You're at rest, and you watch our solar system approach, drift past, and recede into the distance. From your perspective, we're the transient visitors. You're on a long, stable journey, and solar systems like ours are brief interruptions. From 3I Atlas's reference frame, it has probably passed near hundreds or thousands of stars over its lifetime. Some were distant passes where the star was just a bright point of light in the sky. Some were closer, perhaps even closer than our Sun. Each passage was unique, a different gravitational environment, a different radiation environment, a different vista of planets and asteroids and comets. And here's the profound part. From 3I Atlas's perspective, it's our solar system that's ephemeral. We appear, we're present for a brief moment, and then we're gone, receding into the past. 3I Atlas continues on, heading toward whatever star it will encounter next, thousands or millions of years from now. This perspective flip is important because it challenges our anthropocentric view. We think of Earth as permanent and visitors like 3I Atlas as transient. But from a galactic perspective, neither is more permanent than the other. We're all just moving through space and time, occasionally intersecting, mostly passing by. Dr. Leslie Looney at the University of Illinois has been thinking about these issues in the context of what she calls galactic ecology. She argues that we should think of the galaxy not as a static structure of stars and gas, but as a dynamic ecosystem with flows of matter and energy. Interstellar objects are part of these flows, redistributing material between star systems, homogenizing the chemical composition of different regions, creating connections that we're only beginning to map. In this view, 3I Atlas isn't an anomaly or a curiosity. It's a normal participant in galactic-scale processes that have been going on since the galaxy formed. The anomaly is our perspective, our focus on a single star system as if it's an isolated island. In reality, star systems are porous, constantly exchanging material with their surroundings, and interstellar objects are the medium of exchange. And if you zoom out even further, the galaxies themselves are moving. Our Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they'll merge. During that merger, the dynamics will be chaotic, with countless stars having close encounters, and the population of interstellar objects will explode as gravitational interactions scatter material across the merging system. Some of the objects ejected during that merger will be flung out of the merged galaxy entirely, becoming intergalactic wanderers. They'll drift through the voids between galaxies for billions of years, maybe forever, unless they happen to encounter another galaxy and get captured. There might be objects like that even now, refugees from ancient galactic mergers, crossing the vast intergalactic spaces. We'd never detect them unless one happened to pass close to our solar system, and even then we might mistake it for a faster interstellar object from our own galaxy. The universe is full of wanderers at every scale, from dust grains to planets to stars to entire galaxies, all moving through space on journeys measured in billions of years, occasionally intersecting, mostly passing by, creating a vast, slow-motion dance that we're only beginning to perceive. Now I want to explore something that might seem philosophical, but has profound practical implications: the information paradox of interstellar objects. This is your 7th major mind-blown moment. Every object carries information encoded in its physical properties: composition, structure, dynamics, history. When we study 3I Atlas, we're trying to extract this information, to read the story encoded in its atoms and molecules. But here's the paradox. The very act of observing 3I Atlas from a distance means we're only accessing a tiny fraction of the information it contains. Most of the information is inaccessible to remote observation and will remain forever inaccessible unless we physically sample the object. Let me give you an example. When we analyze the spectrum of light from 3I Atlas's coma, we can identify what molecules are present in the gas: water, carbon dioxide, carbon monoxide, and so on. But we can't detect large organic molecules, polymers, or any solid phase materials, except indirectly. If 3I Atlas contains amino acids, we can't detect them. If it contains complex carbon compounds, we can't identify them specifically. And the nucleus itself, the solid body of the comet, is completely opaque to our observations. We can estimate its size from the overall brightness and activity, but we can't see its internal structure. We don't know if it's a single solid body or a loosely bound rubble pile. We don't know if it has layers with different compositions. We don't know if it contains pockets of exotic materials or structures that would tell us about formation conditions in its home system. All of that information exists. It's there, encoded in the physical structure of 3I Atlas, but it's locked away, inaccessible to remote observation, and by the time we develop the technology to send a mission to intercept an interstellar object, 3I Atlas will be long gone. Dr. Lydia Beery at the University of Michigan published a fascinating paper in early 2025 on what she calls the information horizon of astronomical observations. She argues that for every category of celestial object, there's a fundamental limit to what we can learn through remote observation. Beyond that limit, you need physical samples or proximity measurements. For interstellar objects, that information horizon is particularly frustrating because these objects are transient. We can't study them at our leisure. We can't wait for better technology. We get one chance, and most of the information they carry is beyond our information horizon with current technology. This creates what Beery calls an information debt. We're accumulating knowledge about interstellar objects, but we're also accumulating awareness of what we don't know and can't know without direct sampling. The debt grows with each discovery, and we have no clear path to paying it down. But here's where it gets philosophically interesting. Information isn't just about facts and data. It's also about context and interpretation. Even if we could somehow extract every piece of physical information from 3I Atlas, every atom's position and velocity, every isotope ratio, every structural detail, we'd still face the challenge of interpreting what it all means. Consider this. Suppose we found amino acids in 3I Atlas. That's a piece of information. But what does it mean? Did those amino acids form in interstellar space through photochemistry? Did they form in 3I Atlas's home system? Are they the same amino acids found in life on Earth, or different ones? If they're the same, is that convergent chemistry or evidence of common origin? Each piece of information generates more questions, and answering those questions requires context that we often don't have. We need to know about conditions in other star systems, about chemistry in different environments, about the full range of possibilities for molecular evolution in space. In other words, understanding 3I Atlas requires understanding the galaxy, and understanding the galaxy requires understanding many more objects like 3I Atlas. We're caught in a circular dependency where each answer requires information we don't yet have. Dr. Sarah Seeger at MIT, famous for her work on exoplanet atmospheres, has been thinking about this problem in the context of biosignatures and life detection. She points out that when we eventually detect biosignatures on an exoplanet, we'll face massive interpretive challenges. Is that really a sign of life? Or could it be abiotic chemistry that mimics biology? Without additional context, without being able to visit and sample directly, we might never know for certain. The same applies to interstellar objects. They carry messages, but we're not sure we can read them correctly without more context. And getting that context requires detecting and studying many more objects, which brings us back to the detection problem I discussed earlier. But here's an interesting twist that gives me hope. We're not starting from zero. We have one example of a fully characterized solar system, our own, which we can study in exquisite detail. Every comet we analyze, every asteroid we sample, every planet we explore adds to our baseline understanding. This baseline helps us interpret observations of interstellar objects. When we see unusual chemical abundances in 3I Atlas, we know they're unusual because we know what's normal for our solar system. When we see unexpected behavior, we can recognize it as unexpected because we know how our comets behave. Our solar system is the Rosetta Stone that helps us decode messages from other systems. And here's something even more profound. 3I Atlas is helping us understand our own solar system better. By seeing how a comet from another system behaves differently, we're learning what's universal about cometary physics and what's specific to our local environment. We're learning which aspects of our theories are robust and which are based on untested assumptions. In this sense, every interstellar object is like a controlled experiment. Our solar system is the control group, and interstellar objects are the experimental group with one variable changed, formation in a different system. By comparing the two, we can identify which properties depend on local conditions and which are universal. Dr. Alessandra Springman at the Planetary Science Institute made this point eloquently in a recent podcast. 3I Atlas is teaching us about our own solar system in ways we never could have learned by studying only local objects. It's showing us what's contingent and what's necessary in planetary system formation. That's invaluable. This brings me to a deeper point about the nature of information and understanding. We often think of knowledge as accumulation, as adding more facts to our mental database. But real understanding comes from making connections, from seeing patterns, from recognizing what's essential and what's coincidental. Interstellar objects force us to think about these connections because they're naturally comparative. Every observation of 3I Atlas prompts questions like, is this similar to our comets? And what does this difference tell us? These comparative questions drive deeper understanding than just cataloging facts about a single system. In cognitive science, this is called contrastive learning. You learn more effectively when you're comparing and contrasting than when you're just memorizing individual cases. Interstellar objects enable contrastive learning on a cosmic scale. They're nature's way of showing us what else is possible, expanding our conception of what normal means. And there's a moral or philosophical dimension to this as well. The existence of interstellar objects reminds us that our perspective is limited, that what we think of as universal might just be local, that there's always more to learn. This kind of epistemic humility is valuable, not just in science, but in life generally. When we encounter something that challenges our assumptions, like 3I Atlas's unexpected outburst, we have a choice. We can dismiss it as an anomaly, try to shoehorn it into our existing framework, or we can take it seriously as evidence that our framework is incomplete. Good science requires the latter, and honestly, good thinking in any domain requires the latter. 3I Atlas is a reminder to hold our theories lightly, to be willing to revise our understanding when evidence warrants, to remain curious and open to surprises. That's a lesson that extends far beyond astronomy. Let's dive deeper into what 3I Atlas's composition might tell us about chemistry and other star systems, because this is where the science gets truly exotic and mind-expanding. Chemistry, as we understand it, is governed by fundamental laws that are the same everywhere in the universe. The periodic table is universal. Carbon always has 6 protons. Water is always H2O. These basics don't change. But the relative abundances of different elements, the conditions under which they combine, the complex molecules that form, these can vary dramatically depending on local conditions. And those local conditions depend on the history of star formation in a region, which depends on the galactic environment, which depends on the evolution of the galaxy as a whole. Let me break this down. When the universe began, it contained only hydrogen and helium with trace amounts of lithium. That's it. All other elements had to be created through nuclear fusion in stars. Light elements like carbon, nitrogen, and oxygen are made in the cores of ordinary stars. Heavier elements like iron are made in massive stars. The heaviest elements, things like gold and uranium, are made in supernova explosions and neutron star collisions. Over billions of years, as generations of stars lived and died, these elements were scattered into space and incorporated into new generations of stars and planets. But this process wasn't uniform across the galaxy. Some regions experienced more star formation, more supernova, or chemical enrichment. Other regions remained relatively pristine. The result is that different parts of the galaxy, and especially different star systems formed at different times, have different chemical compositions. Stars formed 10 billion years ago in the early galaxy are metal poor in astronomical terms, where metals means anything heavier than helium. Stars formed recently, like our Sun, are metal-rich because they inherited elements from many previous stellar generations. This matters for planet and comet formation because the chemistry available in a system determines what kinds of objects can form. A metal-poor system will have fewer rocky planets and more gas. It will have ices with different compositions. It will produce comets that are chemically distinct from comets in metal-rich systems. Now, here's where 3I Atlas gets interesting. If the preliminary spectroscopic analysis by Dr. Karen Meach is correct, and 3I Atlas has elevated carbon monoxide and methane relative to water, that tells us something about the chemistry of its formation environment. Dr. Edwin Bergen at the University of Michigan, an expert in astrochemistry, has been analyzing these compositional clues. In a paper submitted in April 2025, he argues that 3I Atlas's composition is consistent with formation in a system with a higher carbon-to-oxygen ratio than our solar system. The carbon-to-oxygen ratio is crucial in determining what kinds of molecules form. In our solar system, oxygen is more abundant than carbon which means most carbon ends up locked in carbon monoxide and carbon dioxide, while there's leftover oxygen to make water. This is why our comets are primarily water ice. But in a system with more carbon relative to oxygen, the chemistry is different. Carbon can form more diverse molecules because there's not enough oxygen to bind it all up as CO or CO. You get more methane, more complex hydrocarbons, potentially more organic chemistry. Systems with high carbon-to-oxygen ratios are not rare. We've detected exoplanets with atmospheres that suggest high CO ratios, but we've never had a sample of material from such a system to study directly. If 3I Atlas really did come from a high CO system, it's our first chance to analyze such material up close. And this has profound implications for astrobiology. Life on Earth is carbon-based, using water as a solvent. But could there be forms of life based on different chemistry? Could organisms evolve in high-carbon environments, using methane or other solvents instead of water? This isn't science fiction. Scientists have seriously considered the possibility of methane-based life on Saturn's moon Titan, which has lakes and seas of liquid methane on its surface. The chemistry would be completely different from terrestrial biochemistry, but it might still support complex, self-replicating systems, which is the definition of life. If 3I Atlas came from a high-carbon system, and if such systems can host life, then the kind of life that might exist there would be radically different from anything on Earth. It would use different molecules, different reaction pathways, different energy sources. And if panspermia can occur between star systems, we might someday detect biochemical signatures from such life in interstellar objects, or even contaminating bodies in our own solar system. Dr. Sarah Hurst at Johns Hopkins University, who studies Titan's atmosphere, has been thinking about these possibilities. In an interview in March 2025, she said, "If interstellar objects can carry organic material between star systems, then we need to expand our thinking about what kinds of biochemistry might be possible. We might find molecules in interstellar objects that we've never seen before, that don't fit any of our categories, that suggest forms of chemistry or even life that we haven't imagined." But there's another angle here that's even more speculative. What if some of the molecules in 3I Atlas aren't natural at all? What if they're artificial? Now, I need to be very careful here. I'm not suggesting that 3I Atlas is artificial, or that it was deliberately sent by aliens. There's no evidence for that, and the default assumption should always be natural origins. But it's worth thinking about what we'd look for if we wanted to detect artificial chemistry in an interstellar object. Artificial molecules would presumably have structures that are very unlikely to form naturally. Complex, highly ordered structures. Molecules with properties optimized for specific functions rather than just thermodynamic stability. Isotope ratios that differ from natural abundances because they were selectively enriched. Dr. Avi Loeb has argued that we should be looking for such signatures in interstellar objects, not because we expect to find them, but because the cost of looking is low and the payoff, if we did find something, would be enormous. Even a null result would be informative. It would place constraints on the prevalence of technological civilizations in our galactic neighborhood. Most astronomers are skeptical of this approach, arguing that we should focus on more prosaic questions before worrying about alien artifacts. And honestly, they're probably right. But the mere fact that we can seriously discuss looking for technosignatures in interstellar objects shows how much these objects are expanding our thinking. Here's something that's not speculative at all. 3I Atlas almost certainly contains presolar grains. These are microscopic particles that formed around other stars before our solar system existed. They're identified by their unusual isotope ratios, which don't match solar system material. We find presolar grains in meteorites that fall to Earth, remnants of the original material from which our solar system formed. But those grains have been through the solar system formation process, which modified them. The grains in 3I Atlas, if we could sample them, would be pristine unmodified since they formed in another star system. Each prosolar grain is a fossil from a specific star. By analyzing its isotopes, you can determine what kind of star it came from, how that star evolved, what nuclear processes occurred inside it. You're essentially doing stellar archaeology, reconstructing the life history of stars from the material they produced. If we could collect presolar grains from 3I Atlas, we'd have samples from stars that existed in a different part of the galaxy, possibly at a different time in galactic history. We'd have a window into stellar evolution and nucleosynthesis in environments we can't easily observe directly. Dr. Philip Heck at the Field Museum in Chicago, who has been studying presolar grains in meteorites for years, described the potential in a talk in February 2025. Interstellar objects are the ultimate sampling mission. They're bringing us material from across the galaxy, from different stellar populations, from different epochs. If we could analyze them properly, we'd revolutionize our understanding of galactic chemical evolution. We're approaching the final stretches of this journey, and I want to zoom out to the big picture. What does 3I Atlas, and interstellar objects generally, tell us about our place in the universe? This is where astronomy becomes philosophy. For most of human history, we thought of our world as the center of everything. The universe revolved around us. Then Copernicus showed us that Earth orbits the sun. Then we discovered that the sun is just one star among billions in our galaxy. Then we found that our galaxy is just one among billions in the observable universe. Each of these revelations was a Copernican revolution, a fundamental displacement of humanity from the center of things. Each was initially resisted, then grudgingly accepted, and finally integrated into our worldview. Interstellar objects represent another such revolution, more subtle, but no less profound. They're showing us that our solar system is not an isolated island. It's not a separate, self-contained system. It's a node in a network, constantly exchanging material with a larger galaxy. This challenges the very concept of a solar system as a discrete entity. Where do you draw the boundaries? The traditional answer was the heliopause, the region where the solar wind gives way to the interstellar medium, about 120 astronomical units from the sun. Beyond that is interstellar space, not part of our solar system. But if objects like 3I Atlas regularly pass through, carrying material from other systems, where does our system end and another begin? If there are billions of small bodies ejected from our system, now drifting through the galaxy, are they still part of our solar system? Or have they become something else? These aren't just semantic questions. They're about how we conceptualize the organization of matter in the galaxy. The traditional picture of discrete solar systems separated by empty space is clearly wrong. The reality is messier, more interconnected. Dr. Ruth Murray Clay, who I mentioned earlier, uses the metaphor of ecosystems. In terrestrial ecology, you can identify distinct ecosystems like forests, lakes, and grasslands. But their boundaries are fuzzy. There are transition zones. Species migrate between them. Material flows from one to another through rivers, wind, and animal movements. The galaxy is similar. Star systems are like ecological communities, relatively dense concentrations of material and activity. But they're not isolated. They're connected by flows of matter and energy, with interstellar objects playing the role of migratory species, moving between systems, carrying material and information. This perspective shift has implications for how we think about life in the universe. The traditional approach to astrobiology has been to ask, which planets can host life? We look for planets in habitable zones with liquid water, with atmospheres, and we assess their suitability for life as we know it. But if star systems are connected by material flows, we should also ask, can life spread between star systems? Even if life is rare in origin, could it propagate through the galaxy via interstellar objects, seeding planet after planet over billions of years? This is a testable hypothesis, in principle. If life in the galaxy has a common origin and has spread via panspermia, We'd expect to find biochemical similarities between life on different planets. They might use the same genetic code, the same amino acids, the same fundamental biochemistry, even though they evolved separately for billions of years. Conversely, if life arises independently on each planet, we'd expect much more diversity in biochemistry. Different genetic codes, different building blocks, different solutions to the same functional problems. We can't test this yet because we've only sampled life on one planet. But the framework is there, waiting for the day when we can compare life forms from different worlds. And here's a mind-bending thought. If panspermia occurs, then life in our galaxy might be more unified than we think. Not a single organism, obviously, but a sort of supersystem, a galactic biosphere where material and possibly even genetic information flows between worlds over deep time. In this view, Earth isn't just a planet hosting life. It's a node in a galactic network of living systems, connected to other nodes by tenuous but real pathways. Life on Earth would be part of something larger, a phenomenon that spans the galaxy. This idea was explored beautifully by Dr. Caleb Scharf at Columbia University in his book, The Copernicus Complex. He argues that we need to think about life not just as something that happens on planets, but as a galactic-scale phenomenon, a pattern of organization that emerges from the physics and chemistry of the galaxy as a whole. Now, whether this is actually true, we don't know. It's a hypothesis, an interesting possibility. But the point is that interstellar objects like 3I Atlas force us to consider such possibilities. They expand the scope of what we think is possible, the scale at which we think about biological and chemical processes. Let me connect this to your personal experience. You are the product of 3.8 billion years of evolution on Earth. Your DNA contains information that's been passed down through countless generations, modified and refined by natural selection. Your body is a biological machine of exquisite complexity, the result of billions of years of trial and error. But where did the information in your DNA ultimately come from? The standard answer is that it arose on Earth through natural processes, starting from simple self-replicating molecules and gradually building up complexity. But maybe, just maybe, some of that information has a longer history. Maybe the first self-replicating molecules on Earth were seeded by organic compounds from another star system, delivered by an interstellar object billions of years ago. Maybe the chemical patterns that eventually became DNA had their origins elsewhere, in a different world orbiting a different star. If that's true, then you are the product of not just Earth's evolution, but galactic evolution. Your existence depends on processes that span light years and billions of years, connections between star systems that you're only now becoming aware of. This is what I meant at the beginning when I said that 3I Atlas would change how you look at the night sky. Those stars aren't just distant lights. They're potential sources of the material that makes up your body, the information that makes up your mind. You're connected to them through chains of cause and effect that stretch across space and time. And here's the empowering part. You're now aware of these connections. You understand, at least conceptually, that you're part of a larger system. That awareness itself is significant. It changes how you think about yourself, your place in the universe, your relationship to the cosmos. Philosophers call this kind of realization a sublime experience in the technical sense. It's a feeling that arises when you're confronted with something vast and powerful that exceeds your normal frame of reference. It's simultaneously humbling because you realize how small you are, and elevating because you realize you're part of something larger. 3I Atlas, a small comet from another star system, can trigger that sublime experience if you let it. It's a reminder that the universe is vaster, stranger, and more interconnected than our everyday experience suggests. And you're part of it. Not a passive observer, but an active participant, a conscious node in the network, capable of understanding and appreciating the connections. Let's talk about where this field is heading, because the next decade is going to be transformative, and you're going to be alive to witness it. This is exciting. Right now, we're in what I'd call the discovery phase of interstellar object science. We're detecting these objects, characterizing them as best we can, and building up a catalog. We have 3 confirmed interstellar objects, and possibly a few more candidates pending confirmation. The sample size is tiny, but it's growing. Within the next 5 to 10 years, with new surveys coming online, like the Vera Rubin Observatory, we'll transition to what I'll call the census phase. We'll be detecting interstellar objects regularly, maybe dozens per year. We'll be able to identify patterns, categorize different types, understand the population statistics. This census will answer fundamental questions. How many interstellar objects pass through the solar system each year? What's the size distribution? What are the typical compositions? Are there distinct families with different origins or different properties? Dr. Matthew Hallman's statistical analysis, which I mentioned earlier, suggests that we should expect to find about 1 interstellar object per month once Rubin is fully operational. That's 12 per year, compared to the 3 total we've found in the past 8 years. It's a completely different regime. With that sample size, we can start doing real science. We can test hypotheses about where these objects come from, how they're ejected, how they evolve during their interstellar journey. We can start mapping the galactic flows of material, tracing where objects originate and where they're headed. But even a census won't answer all our questions. For that, we need the next phase, which I'll call the exploration phase. This means sending spacecraft to intercept and study interstellar objects up close. There are currently several mission concepts in various stages of development. The most advanced is called the Bridge mission, proposed by Dr. Artur Devoyan at UCLA and colleagues. The idea is to station a spacecraft in a high orbit or at a Lagrange point, ready to launch on short notice when an interstellar object is detected. The spacecraft would use solar sail propulsion, which doesn't require carrying fuel. A huge ultralight sail would be unfurled, and sunlight pressure would accelerate the craft to high speeds. Calculations suggest that a solar sail could reach speeds of 100 kilometers per second, fast enough to intercept most interstellar objects before they leave the inner solar system. The engineering challenges are significant. The sail needs to be huge, perhaps hundreds of meters across, but incredibly light. The spacecraft needs to be autonomous, capable of navigating and conducting observations without real-time control from Earth. And the mission needs to be affordable enough that governments or space agencies are willing to fund it. But it's doable. Dr. Devoyan estimates that such a mission could be launched within a decade if funding were available. The technology exists. It's primarily a matter of commitment and resources. Imagine what we could learn from a close flyby of an interstellar object. High-resolution imaging could reveal surface features, craters, maybe even areas of active outgassing. Spectroscopy at close range could identify specific molecules that we can't detect from Earth. In situ mass spectrometry could sample the coma and identify complex organics. If the mission included a penetrator or lander, which is more challenging but not impossible, we could directly analyze the nucleus composition, drill down beneath the surface, maybe even return a sample to Earth. A returned sample from an interstellar object would be one of the most valuable scientific treasures in human history. It would be studied for decades, analyzed with every technique we have. We'd learn more about another star system from that sample than from centuries of telescopic observations. But here's an even more ambitious vision, proposed by Dr. Kelvin Long at the Initiative for Interstellar Studies. He suggests that instead of waiting for interstellar objects to come to us, we should eventually go to them. Not chasing objects that are leaving our solar system, but launching probes that travel into interstellar space specifically to find and study these wanderers in their natural environment. This would be a true interstellar mission, leaving the sun's gravitational sphere of influence and entering the realm between stars. The spacecraft would cruise through interstellar space for years or decades, searching for objects using onboard telescopes and detectors. When it found something interesting, it would adjust course to intercept and study it. This is obviously far more challenging than intercepting an object passing through our solar system. It requires propulsion systems that don't currently exist, like fusion drives or antimatter engines. It requires spacecraft that can operate autonomously for decades. It requires solving the problem of power generation far from the sun, where solar panels don't work. But again, it's not impossible. It's just very hard and very expensive. If humanity commits to becoming a truly spacefaring species, missions like this will eventually happen. We'll explore not just our solar system, but the space between stars and interstellar objects will be our guides. Now, let me bring this back to you. Why should you care about these future missions? What do they mean for your life? Here's my answer. These missions represent humanity choosing to understand rather than ignore, to explore rather than stay home, to ask questions rather than accept ignorance. That's a choice about what kind of species we want to be, what kind of future we're building. Every generation faces this choice in different contexts. Your grandparents might have faced it with the space race, the decision to go to the moon. Your parents might have faced it with the Hubble Space Telescope, the decision to invest in observing the deep universe. You're facing it now with interstellar object missions, with the decision to study these cosmic messengers, to build the technology to intercept them, to learn what they can teach us. And here's the thing. These decisions aren't made by scientists or politicians alone. They're made by society as a whole, through a complex process of advocacy, education, funding priorities, and public support. Your interest matters. Your curiosity matters. Your willingness to learn about these topics and talk about them with others matters. If enough people care about interstellar objects, if enough people find them fascinating and want to know more, then the political and financial support for missions will materialize. It's bottom-up, not top-down. The space programs that succeed are the ones that capture public imagination. So by listening to this video, by learning about 3I Atlas, by becoming someone who understands and cares about interstellar objects, you're contributing to the movement that will eventually lead to missions to study them. You're part of the process, a small part maybe, but a real part. And there's something deeply human about this. We've always been explorers, curious about what's over the next hill, across the next ocean, beyond the next horizon. Interstellar objects are the horizons of our era, the unknown territories, calling to our sense of wonder and adventure. We're nearing the end of this journey, and I want to tie everything together into a unified narrative, because that's how you'll really understand what 3I Atlas means. This is your 8th and final major mind-blown moment, the one that connects everything we've discussed into a coherent picture. Here's the story I want you to see. Billions of years ago, in a region of the galaxy, perhaps dozens of light years from where our solar system would eventually form, a cloud of gas and dust began to collapse under its own gravity. This wasn't pure hydrogen and helium like the early universe. It was enriched with heavier elements from previous generations of stars. Carbon, oxygen, nitrogen, silicon, iron, all the building blocks of rocky planets and complex chemistry. As the cloud collapsed, it fragmented into smaller clumps. One of these clumps would become a star, the star we now call Star X in the constellation Cassiopeia. Around this young star, the remaining gas and dust formed a disk, and from that disk, planets began to coalesce. In the outer reaches of this forming system, where temperatures were cold enough for volatiles to freeze, countless small bodies formed. These were the comets and planetesimals of Star X's system, icy aggregates containing water, carbon dioxide, carbon monoxide, methane, ammonia, and complex organic molecules synthesized through photochemistry and radiation processing. One of these bodies, tiny and insignificant, would eventually become 3I Atlas, As the planets of Star X's system grew and migrated, gravitational interactions became chaotic. Large planets scattered smaller bodies in all directions. Some were thrown into the star and vaporized. Some collided with forming planets, delivering water and organics. Some were flung outward into the cold outer system. And some, including 3I Atlas, were ejected entirely, accelerated to speeds exceeding the escape velocity of the system. They became interstellar, condemned to wander the galaxy alone. For millions or billions of years, 3I Atlas drifted through the space between stars. It passed through molecular clouds, vast structures of gas and dust where new stars were forming. It felt the tug of stellar winds, the push of radiation pressure, the occasional impact of high-velocity dust grains. It was cold, perhaps 10 to 20 Kelvin, just a few degrees above absolute zero. Its surface was altered by cosmic radiation, which broke molecular bonds and created new compounds. Amorphous ice slowly crystallized in some regions, releasing tiny amounts of heat that migrated through the nucleus. 3I Atlas was alone in the dark, traveling at tens of kilometers per second relative to the local standard of rest, on a trajectory determined billions of years ago by a gravitational interaction it had no agency to avoid. And then, perhaps 1,000,000 years ago, perhaps 10 million years ago, it entered a new stellar system, our solar system. It crossed the heliopause, the boundary where the sun's influence becomes significant. It fell sunward, accelerating under solar gravity, warming as it approached. It passed through the outer solar system, moving through the realm of Neptune and Uranus, where our own comets and Kuiper Belt objects orbit. If any of those objects noticed it, they gave no sign. It continued inward, passing through the realm of Jupiter and Saturn, the gas giants that dominate our system's dynamics. It felt their gravitational pull, but they were far away, and their influence was minor. It approached the sun, diving to within 0.09 astronomical units, bathed in intense solar radiation. Its surface heated and began to sublimate. Gas and dust streamed away, forming a coma, a temporary atmosphere. For the first time in millions or billions of years, 3I Atlas was active. And then, as it receded from the sun and should have been calming down, something unexpected happened. Internal heat, perhaps from delayed thermal conduction, or perhaps from crystallization of amorphous ice, triggered a massive outburst. The coma expanded. The brightness increased dramatically. For a brief moment, 3I Atlas became spectacular. That's when we noticed it. Humans, living on a small planet in this system, using telescopes built from materials mined from our world, detected a sudden brightening. We analyzed the light, measured the trajectory, realized what we were seeing. An interstellar visitor, a messenger from another star, a fragment of someone else's solar system, passing through ours on a journey that began long before humans existed and will continue long after we're gone. We had a few months to study it, to learn what we could, and then it was gone, accelerating back out into interstellar space, heading toward whatever destination awaits it thousands or millions of years in the future. That's the story. And here's why it matters. This story connects you to the wider galaxy in a direct physical way. The atoms in 3I Atlas are the same atoms that exist in your body. They were forged in the same kinds of stars. They follow the same physical laws. The difference is only in the accidents of history, where those atoms ended up, what objects they became part of. 3I Atlas is not fundamentally different from a comet in our Oort cloud. The main difference is history, trajectory, origin. It's a reminder that the boundaries we draw between our solar system and their star systems are conveniences, not fundamental divisions. At a deeper level, we're all made of the same stuff, governed by the same laws, participating in the same cosmic evolution. 3I Atlas is family, in a sense. Distant, unfamiliar, but ultimately kin, sharing a common heritage in the galactic ecosystem. And this brings me to the final, most profound implication. Your existence is part of this story too. You are made of atoms from multiple stellar generations. Some of those atoms might have been through other solar systems before ending up here. You are a temporary assembly of matter that has a history spanning billions of years and vast distances. Right now, at this moment, you are the universe becoming aware of itself. Your matter organized in such a way that it can think, wonder, ask questions. You can look at 3i Atlas and understand what it is, where it came from, what it means. That's extraordinary. The universe has been evolving for 13.8 billion years, from a hot, dense state to the complex, structured cosmos we see today. Stars formed, planets coalesced, chemistry became more complex, and eventually, on at least one planet, and probably many, life emerged. Life added a new dimension to cosmic evolution. It's matter that maintains itself, that grows, that reproduces, that evolves. And eventually, life became conscious. It began to observe, to think, to understand. You are the leading edge of that process. You're the universe looking at itself and trying to figure out how it works. Every question you ask, every concept you learn, every connection you make is the universe coming to know itself more fully. And 3i Atlas, this small comet from another star, is helping you do that. It's giving you a glimpse of processes that span the galaxy, connections that stretch across light years, timescales that dwarf human history. It's expanding your perspective, showing you that you're part of something vast and ancient and ongoing. This is why 3i Atlas matters. Not because it's a threat in any conventional sense, but because it threatens our complacency, our assumption that we understand how things work. It challenges us to think bigger, to question more deeply, to remain humble in the face of cosmic complexity. And here's the beautiful paradox. The more you understand about the universe, the more you realize how much you don't know. But that expanding sphere of ignorance is actually growth. It's your awareness expanding to encompass more of reality. You're becoming more conscious, more awake to the cosmos around you. Dr. Carl Sagan, who passed away long before interstellar objects were discovered, understood this deeply. He wrote, "We are a way for the cosmos to know itself." Every time you learn something new about the universe, that statement becomes more true. You're not separate from the cosmos, observing it from outside. You're part of it, and your understanding is the cosmos understanding itself. 3i Atlas is a teacher, if you're willing to be a student. It's teaching you about chemistry, physics, dynamics, history, and philosophy. It's teaching you about your place in the universe, about connections you didn't know existed, about possibilities you hadn't imagined. And the lesson doesn't end when 3i Atlas leaves our solar system. The next interstellar object is probably already on its way. Maybe it's decades away, maybe years. Maybe it's already inside the orbit of Neptune, and we just haven't spotted it yet. Each one will teach us something new, expand our understanding further, connect us more deeply to the galaxy we inhabit. Before we move into the final sections, let me give you something concrete to hold on to, because I know we've covered a lot of abstract territory. Let me tell you about something you can actually do, a way you can participate in this story beyond just learning about it. There are several citizen science projects where regular people, not professional astronomers, are contributing to the search for and analysis of unusual objects in the solar system. These projects need human eyes and human intuition to spot things that automated algorithms might miss. One project, called Asteroid Zoo, presents participants with telescope images and asks them to identify moving objects. You're basically doing what astronomers did manually for decades, comparing images taken at different times and spotting objects that move between frames. It's simple enough that anyone can do it, but valuable enough that it contributes to real science. Another project, Comet Hunters, focuses specifically on finding new comets and unusual activity in known comets. Participants scanned through images looking for fuzzy spots that might be cometary comet, or sudden brightenings that might indicate outbursts. Here's why this matters. When the Vera Rubin Observatory comes online and starts flooding us with data, we're going to need all the help we can get to analyze it. There will be too many detections for professional astronomers to follow up on all of them. Citizen scientists will play a crucial role in filtering and prioritizing which objects deserve detailed study. You could be the person who first notices the next interstellar object. It's happened before. Amateur astronomers have discovered comets that professional surveys missed. There's no reason it couldn't happen to you. And even if you don't make a discovery, the act of participating connects you to the research in a direct way. You're not just passively consuming information. You're actively contributing to the collective effort to understand our cosmic neighborhood. Beyond citizen science, you can contribute by spreading awareness. Talk to people about interstellar objects. Share this video. Explain why 3I Atlas is fascinating. The more people who understand and care about this research, the more support it will receive, and the more likely we are to get missions approved to study these objects up close. There's also a practical side to understanding interstellar objects that I should mention: planetary defense. NASA and other space agencies are working on systems to detect and potentially deflect asteroids that might threaten Earth. The current systems are designed for conventional asteroids in bound orbits around the Sun. These objects are predictable. We can track them, calculate their orbits years in advance, and plan accordingly. Interstellar objects are different. They appear with little warning, moving on hyperbolic trajectories that we can't predict until we detect the objects themselves. If an interstellar object were on a collision course with Earth, we'd have much less time to respond than with a conventional asteroid. Now, the probability of this happening is extremely low. Space is vast, Earth is small, and most interstellar objects pass through the solar system far from any planets. But extremely low isn't the same as zero, and responsible planetary defense requires considering all scenarios, even unlikely ones. Dr. Lindley Johnson, NASA's planetary defense officer until his retirement in 2022, has written about this challenge. The protocols developed for conventional asteroid deflection might not work for interstellar objects because of the time constraints. We might need different strategies, different technologies, different response plans. Understanding interstellar objects better, how common they are, what sizes they come in, what trajectories they follow, helps us assess and prepare for this very unlikely but non-zero risk. It's not about fear-mongering. It's about being responsible stewards of our planet. So when you learn about 3I Atlas, you're not just satisfying curiosity. You're building knowledge that has practical implications for humanity's long-term survival. You're helping to create a society that's aware of cosmic context, that thinks on appropriate timescales, that makes decisions with full knowledge of the environment we inhabit. As we approach the conclusion, I want to step back and talk about something meta. What 3I Atlas teaches us about the scientific process itself. Because honestly, this might be more important than any specific fact about comets or interstellar objects. Science is often portrayed in popular media as a steady march of progress, where discoveries happen in logical sequence and each new finding fits neatly into our existing framework. But that's not how it actually works. Real science is messy, full of surprises, constantly forcing us to revise our assumptions. 3I Atlas is a perfect example. When it was discovered, we thought we understood cometary behavior. We had models based on decades of observations. We could predict when a comet would become active, how bright it would get, how it would evolve as it moved through the solar system. And then 3I Atlas said, nope, to all of that. It became active when it wasn't supposed to. It behaved in ways our models didn't predict. It forced us to ask whether our understanding was based on a representative sample or just on the objects we happened to have studied, all of which came from our own solar system. This is uncomfortable, Scientists don't like being wrong. Nobody does. But good science requires being willing to update your beliefs when evidence demands it. It requires holding your theories lightly, testing them constantly, and being prepared to revise or even abandon them when they fail to explain observations. Dr. Thomas Kuhn, a philosopher of science, described this process in his famous book, The Structure of Scientific Revolutions. He argued that science doesn't progress smoothly, but through periodic revolutions, where old paradigms are replaced by new ones. Between revolutions, there's normal science, where researchers work within an established framework, solving puzzles and refining details. But occasionally, anomalies accumulate. Observations that don't fit the framework. Puzzles that can't be solved with existing tools. Eventually, if enough anomalies pile up, the framework itself is questioned, and a revolution begins. A new paradigm emerges that can explain both the old observations and the new anomalies. Interstellar objects might be triggering such a revolution in planetary science. They're anomalies that don't fit our existing framework, which was built on studying one solar system. They're forcing us to develop a new framework that accounts for diversity, that recognizes what's universal and what's contingent. This process is still ongoing. We don't yet have a complete new paradigm. We're in the uncomfortable middle stage where the old framework is clearly inadequate, but the new one isn't fully formed. This is where science is most exciting and most frustrating. And here's what I want you to understand. This uncertainty is not a weakness of science. It's a feature, not a bug. Science is supposed to be uncertain about things we don't fully understand. That's honest. What would be dishonest is claiming certainty when evidence is still incomplete. When scientists say, "We don't know," or "our models fail to predict this," that's not an admission of failure. It's an acknowledgement that reality is complex and we're still learning. It's intellectual honesty, which is more valuable than false certainty. This is important because in the modern world, you're constantly bombarded with claims to certainty from various sources. Politicians claim certainty about policy outcomes. Marketers claim certainty about product benefits. Pundits claim certainty about future events. Science teaches you to be skeptical of such claims. It teaches you that genuine understanding comes with nuance, with caveats, with acknowledgement of what's known and what isn't. It teaches you the difference between confident assertions and well-supported conclusions. 3I Atlas is a lesson in this kind of thinking. When astronomers predicted it, it would behave a certain way, and it didn't. They didn't double down on their predictions or dismiss the observations. They said, "That's interesting. Our model was wrong. Let's figure out why." That's intellectual integrity. And you can apply this lesson to your own life. When your expectations are violated, when things don't work out as predicted, you have a choice. You can insist reality is wrong and cling to your expectations, or you can update your model of how things work. The latter is harder, but more productive. Science is, at its core, a method for updating your beliefs based on evidence. It's a formalized version of learning from experience. And while the specific content of science changes as we learn more, that method is timeless and universally applicable. Let me bring this down to earth, literally, by connecting what we've learned about 3I Atlas to everyday human experience. Because these cosmic phenomena, as remote as they seem, actually resonate with fundamental aspects of human life. Think about the concept of a journey. 3I Atlas is on a journey that spans millions of years and light years of space. It has no destination, no purpose, no goal. It's just moving, carried by momentum and gravity, experiencing what it experiences, until its journey eventually ends, whether by collision, by capture into another star system, or by drifting into the void between galaxies. In a sense, that's all any of us are doing. We're on journeys through space and time. We didn't choose where we started. We don't control most of what happens to us. We're carried along by forces larger than ourselves: history, culture, biology, Physics experiencing what we experience. But here's the crucial difference. We have awareness. We can reflect on our journey. We can find meaning in it. We can make choices that affect our trajectory, at least within limits. 3i Atlas can't do any of that. It's a passive traveler. We're active participants in our journeys, and that makes all the difference. The story of 3i Atlas is also about encounters. This comet has encountered countless things on its journey: molecular clouds, stellar winds, radiation fields, and now our solar system. Each encounter